Rock and roll. Okay, so last time we did the forward solution, sort of thinking about starting with the source in the head and calculating how you get out to the scalp. And part of the reason to do that was to be able to do the inverse, to solve the inverse problem, get the inverse solution. And the inverse solution is try to guess where the activity is given the data on the surface. But before we start that, I just want to go over why should we bother doing this? And this is particularly relevant because if you look at most of the ERP, particularly the ERP literature, and if you look at that, you'll see that that's not the way people do things there very much. So they typically, instead, what they typically do is they look at temporal components. And so there's a very large literature of talking about components as if they were a thing. And what are we talking about here? Typically, we're talking about, across time, we have some time average signal before the event, and so then here's an event, and then after that event, we see some sort of evoked potential. And if you read the evoked potential literature, they treat these inflections in the evoked potential, typically at an electrode or at a small group of electrodes, as a thing. So you might say this is, say, the N100. It's kind of some kind of cognitive processing unit of some kind. I think that's not a good way to look at things. And so why is that? And why do we want to actually localize instead? So the crucial thing that we already know when we were talking about current source density and what the actual response out of a cortical area looks like when you record right in the cortical area. So the first thing, it's extended in time. So it's extended in time, basically, extended in time at every cortical location. So it's extended in time. It's multiphasic, meaning that it sort of goes positive and negative at every location. At every location. So you see like an N1 in V1 and pretty much any cortical area you look at. But the part that's kind of like the most troubling from the point of view of viewing something like this as a component is that the actual signal is temporally non-static. So what does that mean? So basically, an example is if you actually increase the contrast of a stimulus or decrease the contrast of a stimulus or the brightness of a stimulus. So if you change something like the brightness or the contrast of a stimulus, that is going to actually cause huge temporal changes in the retinal response, just the retinal response. So you're going to get you're actually going to get you can get a 50 millisecond delay in the retina if you make the stimulus less bright or less contrasty. if you change the contrast of the stimulus, there's different cells in the retina. Some respond to low contrast, some don't respond to low contrast, and so you can get huge differences in the shape of the waveforms depending on the actual contrast of the stimulus in terms of which retinal cells are activated and which cortical areas they activate. So there's a tremendous amount of sort of flexibility in the actual temporal response, even within a given area, in addition to the fact that every area is multiphasic, every area extends over essentially the whole range of recording. So what does that imply? So that implies, every component of a sort of a temporal component, comes from every area. And this has actually been confirmed by going into the cortex and doing, local field potentials and current source density, in cortex, invasively, like in a monkey. Sorry about that. So what happens if you actually do that? Well, if here's your event. So say we look in V1. So here's the pre-period, and so you get some kind of signal in V1. If you look in V2, this is in a monkey. You get a signal. It's almost the same, maybe slightly delayed. If you look in MT, the signal is pretty quick. But if you look in V4, which is an area next to MT, because V4 doesn't receive very much input from the magnocellular system, the signal, even though it's about the same level in the cortex, the response there is delayed. And if you go to, say, dorsolateral prefrontal cortex, you can see the signal there is actually pretty quick, almost as quick as MT, and quicker than V4. So you're getting a signal from dorsolateral prefrontal cortex. If you go to infratemporal cortex, if the V1 signal is about 50 milliseconds, the IT signal maybe starts about 75 milliseconds. So well overlapping the V1 signal, and so that's what's actually happening in all these areas. And then what do you do? Well, you just add all these up, and what do you get? Well, you get something that looks like that. So you get an evoked potential, but any given piece of it, trying to pick out this thing as a component is kind of, what is it? It's just some sum across all of these guys, across every cortical area, basically. But not only that, if you change the nature of the stimulus and change the distributions of cortical areas, it's going to change the location of that peak, and it's going to change the sign of the peak even. You can easily flip the sign of the peak. So all of these things suggest that this is maybe not the best way to think about this. Now, an alternate method of thinking about it is thinking about it from the point of view of a cortical area, of an actual region in the cortex, a processing unit in the cortex. And the advantage of thinking of it that way is the actual signal that's generated by a particular cortical area or collection of cortical areas is fixed spatially. It doesn't change the way that the temporal waveform will change as you sort of like modulate the contribution of all these different underlying cortical areas to it. So really that's kind of the motivation to try to localize things. It's a better job of trying to sort of figure out what the brain is doing rather than just looking at a summed signal. And one thing that's important, which is I forgot to mention. So every, so a signal anywhere in the brain. So signal anywhere. A source, a signal from a source, signal anywhere. So signal from any source appears on all electrodes. And that's mainly because of the fact that you've got this very high resistance skull, and so if there's a signal coming out of here, the current is going to tend to sort of flow along, a long distance that way. And so the end result is that essentially every electrode, a single electrode sees every cortical area. And so even if you just pick out an electrode, say like I go to a temporal electrode and I say I'm doing temporal things, temporal electrode is going to see stuff in the frontal cortex, is going to add in to it. So that's the motivation. Let's sort of get beyond components. There's like a giant literature of sort of trying to attach psychological functions to individual components, these temporal components, and I think we can do better. So how can we do better? Well, there's certain, and why haven't people done this? It's a little technical, and there's certain kinds of problems that come up when we start to look at the inverse problem that makes it a little difficult to localize deep sources. It makes it a little difficult to localize things nearly as well as fMRI does. But nevertheless, the bottom line is you can still break up the brain into 30-ish different regions and look at how these things interact with each other across time, and in particular, how do simultaneous areas come on at the same time? Because basically almost everything that is happening in the brain when you do an event is overlapping. All these areas are generating an overlapping signal. And don't just think of V1 as an input area. Stuff, goes up and comes back to V1, over time, and you get a lot of sort of circulating processing that goes like top down and bottom up. And so if you want to be able to see any of that, then you really need to kind of try to figure out where these things are coming from. So we'll start with the good, the good news, which is that everything is linear. So here's a voltage at a given sensor. So we'll use I to mean, or the ij in a matrix. I is the rows and columns. So I are the rows, and so this guy, the I are the sensors, okay, or electrodes. Could be MEG. So that's sensors, and so this is what you get at a sensor is basically just the linear sum of those forward solutions for each source. And so here's the forward solution for each source sensor pair. So ij means that you've got all the possible combinations of sensors and sources. And so here's the J. So the J is, it's not a J. Okay, so here's the J, and the J are the sources. So this is sources. And then the E is basically the forward solution. So this guy is the forward solution. So that was the source for the EEG is the source strength times the vector that goes to the recording site dotted with the dipole location and length dotted with the vector that goes to the recording site divided by the distance cubed plus all the corrections. So that was the brain fills the universe plus corrections. So that's the forward solution. So that's a single number. So that's just a number. It's not. It's just a weight, basically, that you multiply by the source strength. So this is the source strength at a moment in time. So source strength at time point. So time doesn't appear in this. This forward solution works for sort of instants in time. It's all spatial. So at each instant in time, you calculate a new signal. So this is, signal at sensor. The I is the sensor index, but this number here is just, in the case of the EEG solution, it's just a potential at a particular point in time. And how do you calculate that? It's just it can be calculated for each instant in time as this forward solution weight. So you can think of this as the weight for a particular sensor source pair. Weight for sensor source pair. So for a particular dipole, somewhere in V4, that's a source, and for a particular electrode, wherever it is, electrode 13, there'll be one number. So that's our forward solution. And then last but not least, we've got some noise in there. And so the noise, sensor noise, so that's as the index of sensors. So that's our forward. So that's a very simple forward solution, which we can write as an actual matrix. I'll just write it down below here. So we can write this out as a matrix. So this guy's a matrix, but this guy's a vector. So if we write out our electrical forward solution, we get sort of a vector like this. So here's our V for voltages, we'll say. So that's our data at each electrode. And what is that going to equal? It's going to equal basically just a matrix. This is another way of writing a matrix multiply. And so if you write a matrix multiply, we're going to have our forward solution. And our forward solution is going to have sensors going in this direction. So we don't have too many sensors. This is sensors going in this direction too. So that means just, however many electrodes we have. And then the matrix is going to be really long this way. So why is it long that way? Well, it's long because we are thinking of our sources as basically we reconstruct the cortex, and then at each little patch of the cortex, we divide the cortex up into a whole bunch of little patches, like a couple thousand patches, and then at each patch, there's basically the possibility of a dipole, and the direction is going to be perpendicular. That's because of our knowledge about the current source density, and it could have an amplitude, which is this source strength. That means how long is the vector, but you can't rotate the vector. It's just fixed perpendicular to the cortex at that point. So if we look at this forward, so it's much wider than this because there's it's 5,000 by a couple hundred this direction. But I'll just draw it out as sort of rectangular this way, not hugely rectangular. And so this is our E, matrix, And so what's in the E matrix? It's going to be sources going this way. The columns are sources. And if we look at a row, if we look at one row, like what is a row? So one row is going to be the weights for one sensor, the forward solution weights for one electrode. So that means like you just look at every possible location. What is the simple number weight of how much of a signal that's going to give for that particular sensor? And then if you look at a column is the opposite thing. That's basically the weights for one source. So this is weights for one source. So there's less of those because that's for a given source. What do you need to multiply to get the voltage at each sensor? So that was just the E. I just made that, just turned the E from this notation into a matrix, and then you're going to be multiplying by the same distance here. So you're multiplying by your sources, and this is going to be much longer than this in real life, but that's all the simple scalar amplitudes of all the sources. And so this is this is sources going this way again. And then finally we have some noise. So plus a noise vector, and the noise vector is going to be the same size as the sensor vector because this is the sensor noise. So here's our noise vector. So that I used E to mean sort of electrical forward solution, but then we have the problem of what if we want to combine possibly magnetic recording, like MEG recording. So in that case, what's going to happen is we're going to have more data. And in fact, depending on exactly what the configuration, remember the magnetic sensor data is a vector, so there's potentially 3 components of that, whereas the electrical sensor data is just a voltage, and so that's just a single number. And especially if you're working with MEG, it's not uncommon to put on, say, 30 electrodes or 60 electrodes if you're working with EEG. But with MEG, you can easily get a couple hundred sensors because they're all just in this helmet, and so you can just put the person in the helmet. And so there's going to be another addition to this vector, and that we'll call that one the M vector for the magnetic vector sensor. And so then we're going to have to expand our forward solution, because then we're going to have a B for our magnetic forward solution. But the magnetic forward solution, once we fish out the sensors into their components, like the XYZ components, this thing will still just be a number. So if you're detecting the magnetic field, say, going in this direction, it will just be a single. This forward solution would just be a single number saying how much does a given dipole cause a magnetic field in that direction, and that's just a number. Okay, so that's basically. Let me just make this guy a little longer so that you can see it's not the same length as that one. Okay, so the number of sources, however, doesn't change because one source, is causing both EEG and MEG. It causes, both MEG. So, so basically you won't change the number of sources, you just increase the number of data points, which is good because, there's more of these sources than there are data points. And then we would have to increase the noise because there's going to be some magnetic noise. So this is, noise M. This was noise, E. So that's our basically our forward solution. Just what we talked about before, a linear forward solution. And so we can summarize that as X, meaning magnetic plus electrical, equals A, meaning electrical plus magnetic forward solution, times the source vector plus the noise. So now we've got it all down like mathematicians like to do, down to just a couple letters. So that's an extremely simple forward solution. So this is mag plus or EEG plus mag. So that's good. And this is also, E plus B. And so here's our sources. That's what we're solving for. And noise. So what is the inverse in this very simple linear case? What is the inverse? Or how do we solve for the inverse? So if you look in my notes, there's a lot of literature out there on trying to solve these kinds of linear problems, and the way that Anders Dale and I originally got the solution, which was to actually just view it as kind of like almost like a neural network error correction. So you write out an equation for the error and just try to figure out what direction should we go to reduce the error. That's actually how this was derived. So let me just write out the inverse solution. But before I do that, I should just write out what is the inverse, just like what does the matrix of the inverse solution look like. And so what that will look like is it's going to be something. So what are we going to do with this equation? We just want to solve for this. Now, there's an obvious problem here. If we've got, say, 8,000 sources, and maybe we've got 200 MEG and 30, so we've got 230 data points. Obviously, how could we possibly solve for 8,000 sources when we've only got 230 data points? It's completely impossible. And that's what's basically called an underdetermined problem. It's an underdetermined problem because we don't really have enough data. And so we're going to have to somehow add in some information. And so we can add in information like what is our expected variance of the sources, or what is our expected noise going to be like? And then we can do something, we can add in a critical thing called a minimum norm solution. So a minimum norm solution is a solution that picks out one of the infinitely many possible solutions that you can get subject to a constraint. And that constraint is basically the smallest solution. And so that's the one that you get if you try to solve this problem. It's called a minimum norm solution. And so if you look at what that looks like from a matrix point of view, it kind of looks ungainly because now you've got this long vector of sources. So that's your answer. And so that long vector of sources is going to be equal to a rectangular matrix going the other way, which is our we'll call that W matrix for our inverse. So this is our inverse solution. So that's our inverse solution. After we solve this, we get this other matrix rectangular the other way, and everything's linear. So basically what we do is we just take our sensor data. So here's the the V and the M data. And how do we get our solution for a time point? So remember, again, this is, inverse. So inverse solution, this is the inverse solution matrix, but that's fixed, fixed across time. So it's fixed across time. So here's this is an inverse solution for a single time point. So the idea is essentially you solve this this forward solution for the S, try to figure out the S, and what you end up with is a matrix that you can multiply your data by to get this S. So that's the solution. So you're solving for this guy, and so you end up with this matrix. Now we didn't explain what this matrix is. So what this matrix is something that we do to the data that we have, plus whatever additional assumptions that we might stick in there. And so we'll just write up that. So let me just make sure so this is sources going this way now, and this is sources and sensors going this way, and then this is sensors again. So in real life, this was going to be like 5,000 long that way, but just a couple hundred this way. So what is the actual inverse solution W look like? So that W looks like. So if you look in the notes, you can see how this is derived, but it's got a couple. So these are all matrices. So these guys are all matrices. A you recognize because A is that forward solution. T means the transpose of it, just sort of turn rows into columns. And times A R A transpose again. Inverse of that. So that's a matrix inverse. Plus a C. Oh, sorry, put that in the wrong place. ARA plus C inverse. Okay, so there's different ways of solving this. You can solve it with you can pose it as a Bayesian problem, and you get a different equation, which turns out to be mathematically equivalent to this one. This one's actually easier to. This sort of error minimization approach gives you an equation that's easier. It gives you an inverse that's easier to solve, a smaller inverse. But what are the things in here? So this guy is the forward solution. So that's just all those numbers that we calculated by making a model of the head and figuring out where all the dipoles were and what is the weight between each dipole and each sensor. But there's a couple extra things in there, and so one of them is C. And so this one is our assumed. So that's kind of some prior information that we're sort of adding into the solution, which is our assumed sensor noise covariance. And so what does that mean? So what that means is you've got a matrix that is basically sensors by sensors. So it's a diagonal matrix. So down the diagonal you'll have the variance of each, your expected variance of each sensor. So this is var. That's kind of the correlation of a sensor with itself of each sensor. And then all these points here, they'll be symmetrical. It's a symmetrical matrix, so these two, if you correlate this sensor with that sensor, it's equivalent to correlating this sensor with that sensor. So it's a mirror image matrix across the diagonal. So those things are the covariance of the sensor. So what does that mean? That means if you've got some noise in the sensor that's not due to the brain, how correlated is one sensor with another? Because maybe the sensors interact with each other a little bit, or maybe there's some noise. Now, you might think, well, how could we possibly know that? That's something you can actually measure. You could actually just stick nothing, like don't put any head into the sensors, or just put a head that doesn't have any brain in it, and then just measure the noise in your system and just see whether there's any tendency for sensors to be correlated with each other. And then what about the variance? Well, that would be if you think that one sensor is going to give you a bigger signal than another sensor. But if we want to be very conservative, we could just say, everybody has an equal likelihood of having variation in it. That's along the diagonal. And then zeros, we will assume there's no correlation between any sensor and any other sensor in the noise. So that's some additional information that we kind of added in to help us out a little bit. But then there's another matrix here, which is this R matrix, and that R matrix is basically the assumed source covariance. And so what is that? That's going to be a bigger matrix because it's sources by sources, because this was sensors, right? Sensors by sensors. This is source by source. So this is the bigger one. And so what is this? So again, this one has on the diagonal, it has, what do you think the actual sources are going to be, the variance of different sources? So you might have some information about this. For instance, maybe you've got some fMRI data, and you think that, this source is more likely to be active. So we could put in some fMRI data. But again, if you want to be really conservative, you could just say, so once again, this is the variance of the sensors, and the whole rest of the matrix is the covariance. And so we could just assume the covariance, for instance, equals 0, and the variance, is the same for all. That's conservative. So we just assume we don't know which source is going to be active. We'll just allow them all to be the same. So when you look at sort of geometrically what's going on with this particular solution to the inverse, what's actually happening is you've got 8,000 unknowns and 230 data points. And so there's going to be infinite number of different possible solutions. And so what the minimum norm is basically pick solution, what the meaning of it is. This is the minimum norm solution. What it means is pick solution S, with smallest norm. And so what is that? That just means you just sort of add up all the individual components of the solution and then figure out the Euclidean norm of that. So it just means like take your S solution vector and then just calculate the norm of it, just the Euclidean length of it, after including all the different dimensions. That's actually what it is. So why is that a good thing? Well, that's a very sort of conservative kind of solution. It picks out a solution out of the infinite possible that has the smallest size. That's the most likely one to be correct because there's always a finite amount of noise in your system. The problem with it, so if you look at this solution, it sort of seems like it misbehaves. And so let's just take an example of how the minimum norm solution will work. So if we start off with a superficial source, so let's start off with a superficial source. If you start off with a superficial source, works pretty well. So the idea is we put sources all over the place for where the data could appear, but we will, so say here's the head. So we put a source up near the surface. We allow sources to be everywhere else. And then, so that source, so this is a modeling study. So just insert a source there, calculate the forward solution, and then do the inverse. And what will happen, you'll actually do pretty well. So, you might get, the source is going to spread out a little bit like that. Not too bad. But most of it will be in approximately the correct place. So this is the solution. This is our actual meaning because we did a modeling study. So we actually put the dipole there. Our solution sort of came out approximately correct. We allowed the solution to be anywhere. So throughout the whole brain, there's 8,000 dipoles, and it could be anywhere, but it comes out approximately in the right place. So that's good. So that's a superficial one. But it sort of seems to horribly fail with a deep solution. And so how does it actually fail? So, well, it doesn't fail. It actually does the right thing. So if you look at a deep, so now let's put a deep dipole, same dipole there. And if we calculate the forward solution for that, it's going to be a much smaller signal because remember there's an inverse square thing going on. Inverse square. So as you go deeper, the signal gets much smaller than when you go superficially. So what happens when we calculate the inverse of this one? Well, now it doesn't look so good. So now what happens is you get a bunch of tiny little dipoles right at the surface. So maybe you've got some cortex like that. So it won't put it down in the sulcus. It'll just put it right up on the surface. Let me just draw that a little bit better. So here's our cortex in there. So what will happen is you'll get a tiny little dipole there, nothing down there, tiny little dipole here, it'll smear out the signal over a huge area, completely get the thing in the wrong place. So here's our actual dipole. So same size dipole. We just put it deeper in the brain. And so if you look down where it actually is, you'll see there'll be a tiny little guy down there, even smaller. And so the question is, why did it do this? This is actually the right answer. And why is it the right answer? Because it's hard to see these guys. So they're more likely to fall into the noise. And so but why does it pick this solution versus the one down there for the most part? It picks it because it has a smaller norm. And why does it have a smaller norm? Because of the inverse square. So this solution has a smaller norm. And that's because of the inverse square property. So you can get away with a smaller total solution size by putting them all up here. and model that data, then if you put a nice big, a single big dipole down there, so the overall norm of the solution will be smaller because of the inverse square. Because we could put, I didn't draw it exactly to scale, so these are really, really tiny compared to this big one down here. And the total norm of these guys will be less than that. So when people first figured this out, they said, oh man, this is a terrible solution. So how are we going to fix this? So one of the ways of fixing it, the first urge is, well, you're discriminating against the deep dipoles. So let's just turn up their variance. So we could just turn up their variance and say, we'll just add higher numbers along the diagonal for the source covariance matrix for the variance. That's the diagonal as the variance. And then that will fix the problem. And if you do that, then you'll get the correct solution because you've added a little extra, you've given them a little advantage. But that's not the right thing to do, because then if you just put noise, if you just generate random noise for your data, run it through this inverse solution with emphasize deep sources, you'll get deep sources. So it's obviously going to insert a prior expectation that there's more deep sources than superficial sources. That's clearly not right. So what can we do? So a lot of people, when they first looked at this, said, I just don't like it. I'm just not going to localize. But the one way that Anders Dale came up with is to look at how we might view this solution. And so this idea is to do what he called noise normalization. And so one of the things when you look at this picture, you do see a little tiny bit of signal. I drew it too big. You do see a little tiny bit of signal at the correct place. It didn't completely throw it out. It just said, I think it's more likely that there's going to be signals at the surface because I can get away with a smaller norm for giving me that surface one. And so what is the plan? So the plan was basically just to find a way of viewing the solution that shows you these small but significant deep signals. And so the way that you do this is you essentially just, that's why it's called noise normalized. So if you, shouldn't have erased that, the inverse one, but let's just put that one back up again. So here's the sources, and here's, sources equals our inverse matrix, W times our data, so V and M. So this is a time point. So what you can do, a very straightforward thing to do is just take a row. So if we take a row out, if we put an index on the matrix, that means, it's an I, that means let's just get one of these. So this is, I, and this is J, going in that direction. So this means get one row out of the matrix. And if we just take that inverse solution row of weights and just divide it by, it's a very straightforward thing to do, just divide it by the norm of that row. So what does that do? So what that does, so normally if you look at what we said when we're looking at the inverse problem here, what we said was that why does it pick the superficial one? It picks the superficial one in addition to the deep one because the norm is smaller. Why is the norm smaller of that superficial solution? Because of the inverse square. Because as you make dipoles go deeper, they fall off really quickly. And so you can always get away with a smaller solution by using these dipoles up near the surface that don't fall off because they'll be very visible in the signal. So if we divide by the strength of our inverse solution, this strength of our inverse solution is going to be small because of this minimum norm thing. If we divide by a small number, it'll sort of beef it up a bit. So the bottom line is it will give us it will allow us to look at the inverse solution and detect cases where there's a small bit of signal down there in the right place, but it's kind of swamped because you see this big signal that all got displaced to the surface. But if anything appears down there, it's very significant. So this is our equals our, noise normalized. So this is our noise normalized inverse. And so what does this do? This is not, it's only for viewing, for viewing pleasure. It's like a stat. It's not the actual inverse. So it's actually just a way of looking at the inverse, and then you can actually detect, is there something, a tiny bit down there that if anything appears down there, it's very significant because it's really hard to see stuff down there. But what you get after applying this inverse instead of using the real one, you don't get a solution. What you get is a way to view the solution. So what does that look like when you actually say you've got a superficial source here. What's going to happen if we just do a modeling study and apply this? So if you do a modeling study and just do the regular solution, so this is just using the regular real one, you're going to localize that superficial source pretty well. If you use the noise normalized one, we'll just call it norm for short, what you're going to do is you'll actually kind of smear out that solution a little bit. So that's for a superficial. For a deep one, however, you will actually sort of rescue the deep one and make it visible. So this is a deep one. So what happens for a deep one, say you've got a deep one down in the insula, which is kind of a deep area. So what happens? So this is a modeling study with just a single source, single superficial. So if you do a regular inverse solution, what will happen is you'll just smear that whole signal out to superficial. You won't get hardly any in the deep place where it's supposed to be. It will just be displaced to the surface, spread out over a large area. If you, however, do our, so here's that, we'll put that in the insula. That's kind of the insula, somewhere down in the insula, which is deep. So if we do our norm one, what will happen is you will put it back down in the insula. You'll spread it out about the same amount as this, and you'll be able to see it. It will sort of like be properly visible. Now remember, that's not the solution. It's just for your viewing pleasure. It's not the actual solution. The actual solution is this thing, is the minimum norm with most of the signal displaced to the surface. But this, you can sort of think of this, you can think of it like a stat. It's kind of, how significant was the response, ignoring its size. So if you get anything down there, even a tiny bit is quite significant because it's quite hard to see stuff down there. So that's one sensible way of dealing with this, this inverse solution. And what does it allow you to do? What's the bottom line? So the bottom line is it allows you to basically divide the brain up into like 20 or 30 regions. Now, of course, so it's going to allow you to sort of basically, you'll be able to distinguish sort of occipital stuff from sort of dorsal occipital stuff, from sort of interparietal stuff, from slightly in front of interparietal, maybe stuff down in the central sulcus, stuff in the superior temporal junction. You could sort of pick up stuff in anterior, temporal, or maybe more auditory. So it's going to divide the brain up into, 1 to 2 centimeter chunks. Just bail on really deep. So anything that's very, very deep, it's just a lost cause. If it's more than, say, like, more than 2 centimeters. But it turns out that, the cortex, you're probably getting 70% of the cortex, something like that, 70, 80% of the cortex. So, and then what's the real big advantage over sort of this component thing? Well, these are real components. These aren't fake temporal components that come and go and sort of are the sum of 20 areas piled on top of each other with slightly different temporal relations causing the peaks to change and move around. These are actual real components. It's actually stuff that came out of this part of the brain. And so you can sense, well, these guys are on at the same time. That's something you can't do with the regular components. You just have a component. You say, well, I did some experimental manipulation and it changed my component. Here you can say, this one came on first, then this one came on and this one stayed on. So there's some processing going on in both of those at a particular time point. So it's a big advantage to do this. So why don't people do it? Well, they often don't do it because it's a pain in the butt. You've got to recover the cortical surface. You have to record the 3D locations of your electrodes, relate those to the cortical surface. And it's a little more work. It's got these problems that you can only localize to 1 or 2 centimeters. You can't really see the deep sources. You're only seeing the radial components. All these things sort of seem bad. Those are all there when you're doing components. It's just like you're just brushing it under the table. This is what you can actually see. This allows you to actually sort of see information flowing around in the brain in real time across these different areas with real components. The components are actual spatially localized chunks of the cortex. So that's my sermon for today, why everybody should start to do this. Just for sort of one historical note, doing this is the whole reason that we wrote the FreeSurfer software for reconstructing the surface, because that was actually written before, unbelievably, before fMRI. BF, yes, before fMRI. So all the cortical surface reconstruction software was written for this purpose, for localizing EEG and MEG. And then when fMRI came along, we said, oh, that's a lot easier than EEG, MEG, so we'll do that instead. So, okay, so let's David end the recording there if it's still actually going.